Hello. Here will we be solving for the video presentation 1 problem. First, we're going to draw a quick diagram. So, in our problem statement, we're given the diagram and we are given strain. So we have epsilon A equals 475 times 10 to the 6. Epsilon B is 200 times 10 to the negative 6. And epsilon C is negative 250. So we're asked to find sigma 1, sigma 2, and so the normal stress, max and min, and our shear stress. And we're going to do this using Morse circle for our stress transformation. We also know that we are using AISI 302 steel, stainless steel. Looking up in the appendix, we know the modulus of elasticity is 2800 KSI. Modulus of rigidity and Poisson's ratio. So let's get started. First, we're going to use a system of equations in order to find our sigma x, sigma y, and gamma xy. Sorry, epsilon x, epsilon y, gamma xy. So we're going to do that using these equations. Sigma x cosine 2 theta, and that's 4a, plus sine 2 theta, gamma xy, cosine theta, sine theta. Looking at our angles here, we know theta A equals 0, theta B 60, theta C 120. So we have 0 degrees from the x-axis, 60 degrees, and then 60 plus 60 is 120. Solving this guy, first of all, we can see from our diagram that epsilon A is actually going to be epsilon x, because cosine of 0 is 1, sine of 0 on both of these is going to make these 0. So we can just show that plugging it in. So these are going to go away. And this is going to be 1. So that gives us EA equals EX, epsilon A equals epsilon X. So we know that epsilon X, 475 times 10 to the negative 6. Now we're going to do the same thing for B and C and make a system of equations and solve for that. So now we have epsilon B that's 60. Okay. Next, we know epsilon B and epsilon X. So this is going to be 200. Epsilon X is 475 times cosine of 60, cosine squared 60. Is 1/4. Now we got epsilon y, our unknown variable, one of the unknowns, sine squared 60 0.75 plus gamma xy cosine 60 sine 60. That gives us 0.43. So simplifying this, that's right, I think. Oh no, we got to evaluate this 1/4 before we do that. So that's going to be sorry about that, 119 times 10 to the negative 6. Don't know why that took me so long. Simplifying that. This becomes 81 times 10 to the negative 6 on this side, and then on the other we have epsilon y 0.75 plus 0.43 gamma xy. So we have two variables that we need. We're gonna have one more equation, so let's set this in terms of epsilon y. And that's going to be times 10 to the negative 6 minus 0.43 gamma xy divided by 0.75. All right, moving on, epsilon c, same equation, new angle. We know 475 times 10 to the 6, cosine squared 120. We have epsilon y now, so we're going to plug that in. then we finally have, oh, and this is also times sine squared 120. And then finally, gamma xy cosine 120, sine 120. Okay. We also know EC, so we can simplify this. Epsilon C, excuse me, negative 250. And then we got 475. So this is going to be 119 times 10 to the negative 6. This is going to be so actually sine squared 120 is 0.75, so those are going to cancel. And we're left with this top guy. Then we got cosine 120 times sine of 120. That's the same as this guy, so negative 0.43 gamma xy. All right, simplifying. We're going to be solving for gamma xy here. So these are going to be negative 450. These two added together are 0.86. Yep. Negative 0.86 gamma xy. So from this equation, we can get gamma xy. So this value is going to be times 10 to the negative 6. Okay, now we're going to plug this guy into here. So we have epsilon x, epsilon y, gamma xy. Let's go ahead and do that. Seven. 0.75. So this equals is going to give us negative 192, 10 to the negative 6. All right, so you can see we have these three. Now we're going to go ahead and use our generalized Hooke's law equation. That's defined as sigma x e epsilon squared. And these we've gotten from our material properties up here. Okay, and then, so for the x direction, it's going to be epsilon x plus Poisson's ratio, epsilon y. We can go ahead and solve that guy. This is going to be I think this should actually not one extra zero on there. I think. Let me double check. Yeah, so it's actually going to be this, according to our Appendix B. Okay, so moving on. Over 1 minus 0.27 squared, Poisson's ratio, times epsilon x, 475 times 6, plus Poisson's ratio times epsilon y, 192 times 10 to the negative 6, all right. So we got 475 times 10 to the 6 plus 0.27 times. This gives us normal stress, X, or sigma 12.8 KSI. We're going to do the same for the Y, slightly different equation, very similar, except this time we're going to have Poisson's ratio times the X. And not the Y. All right. Solving for this. Times 470. This is going to give us sigma y negative 1.92 KSI. And fit this in, sorry about that. So we got sigma x 12.8, sigma y 1.29 negative. And we also have this equation for shear stress tau xy, which is G gamma xy. So our modulus of rigidity, as we set up here, times, where is it? xy. This is going to give us 5.65 KSI. All right, almost there. So now we know sigma x equals 12.8 KSI. Sigma y equals negative 1.92 KSI, and our tau xy is 5.65. Yep. All right. Let's go ahead and calculate our normal stress average, because we're going to use that later for our Morse circle. This gives us an average value of 5.44. So for our coordinate system for our Morse circle, we got x, y, and the center point. So the x is defined as normal in the x minus shear. Y is normal in the y. Shear. Center is our average, and then 0. All right, so this is going to be 12.8. And it's going to be negative 5.65. We're going to go negative 1.92, 5.65, and our 5.44 average value, and 0. So now we're going to go ahead and draw our Morse circle, and this is going to be for our stress transformation step. So hopefully you can see. Yep. So our center is going to be 5.44. That's about, we can eyeball it. Center. And then go ahead and draw a circle. My lines are not straight. It's kind of a bad circle, but you get the idea. Okay, now we're going to go ahead and plot our x and y. We already have our center point right here, 5.44. So we're going to go 12 about and down 5.65. We can call that here. And then we're going to go negative 1 point. Oh yes, and our axes for this Morse circle. Almost forgot. We're going to have normal on the x, shear on the y. So it's plotting that relationship. And so yeah, negative 1.92, and then up, same amount. So point F and point G. Okay, so using this circle, now we're gonna use this to find our radius, and this is gonna solve the problem with our average value. Almost there. R equals, we're given the equation for a radius is, I believe, CF squared, CF and FX squared, so that we're getting our radius right here from the center. Some simple trig. All right, so CF, distance between C and F, 12.8 minus 7.36 squared. This is going to be 5.65. Square root of it all. All right. So our R value is going to be 9.27. Alrighty, so now we're gonna solve. This is our max normal stress, which is the average plus the radius, which is gonna be 5.44. So this is our first answer in KSI. 14.17, just adding the average normal stress with the radius from our Mohr circle. This is our minimum shear stress, which is going to be similar equation, average minus, this time, R. That's the difference, plus and minus R. So we're gonna get negative 3.83. And then our last step of the problem, tau max, which is simply just R, 9.27. And there we have it. We have both stress min and max, or 1 and 2, and shear stress, maximum shear stress. Thank you for watching. This has been video presentation 1. Have a good day.